Welcome to Dreaming Through Knowledge. Tonight, a single raindrop is followed on its long and endless journey, from the high quiet of the sky to the open skin of the earth. If these journeys bring calm and curiosity, follow the channel and share in the comments what you would like to discover next. The story of a raindrop begins in silence, high above the ground where air grows thin and temperatures slide below freezing. Water lives as invisible vapor. Molecules drift freely, spaced far apart, carried by winds that flow like slow rivers across the sky. In this pale region, the sky carries more than color. It carries the beginnings of every river, every lake, and every breath. Air can hold only a limited share of vapor before it becomes saturated. When warm, moist air rises, it expands and cools, and its capacity to hold vapor decreases. Molecules slow, cluster, and settle onto tiny seeds that float everywhere. Dust, sea salt, smoke, volcanic ash, pollen. These particles are called cloud condensation nuclei, and each one is a scaffold on which a droplet may grow. A cloud is not a solid object. It is a region of air where billions of microscopic droplets and crystals remain suspended by rising currents. Most droplets are smaller than 1/100th of a millimeter, so small that gentle updrafts keep them aloft with ease. Together, they scatter sunlight in all directions, softening the sky into white, gray, or pearl. From the ground, a cloud seems heavy, yet the total water inside a fair-weather cumulus could fill only a few swimming pools spread across a towering volume of air. Two main pathways feed these clouds. In warm clouds, droplets grow by collision and coalescence, small drops bumping into larger ones and merging into beads with more weight. In cold clouds, the Bergeron process favors ice. Water vapor deposits onto tiny ice crystals more readily than onto liquid drops. Crystals grow into plates, needles, and dendrites, then fall and melt into rain if they pass through warmer layers below. Inside the cloud, air moves constantly. Updrafts carry droplets upward into cooler layers, downdrafts bring them back down, and shear stretches the field into cells and filaments. The droplets collide again and again, some merging, some bouncing, some shattering into smaller pieces that begin their gathering anew. Each second adds or subtracts microns of size. When a droplet grows beyond a critical size, gravity gains the advantage over lift in the surrounding air. The fall begins. At first, the drop is nearly spherical. Then air resistance flattens its base. If it grows much larger than 3 millimeters, the rim ripples. A thin ring waves and breaks, and the drop splits into smaller daughters that continue the descent. This is where the journey becomes visible. A typical raindrop that reaches the ground measures about 2 millimeters across and falls near 9 meters per second through still air. In gusty air, the speed varies, since rising currents slow the fall while downdrafts quicken it. The surface quivers, oscillating between squat oval and rounded cone as pressure changes slide across it. The path from the cloud to ground is not a simple line. Layers of air differ in temperature and humidity. As the drop falls through dry air, molecules at its surface escape into vapor, a process called evaporation, and the drop shrinks. When humidity climbs toward saturation, evaporation slows and the drop holds its size. In very dry layers, falling drops can evaporate completely before reaching the surface, leaving gray curtains that hang beneath clouds and fade into air. This phenomenon is known as virga, rain that falls and returns to vapor before it touches the ground. In winter, the same descent follows different rules. If the cloud is cold and the air beneath it remains below freezing, crystals keep their shape, drifting as snow. If the crystals melt in a warm layer, then refreeze in a shallow cold layer near the surface, pellets of sleet form that bounce on roads and windows. When rain freezes on contact with a surface that is still below zero, a glaze of ice appears, called freezing rain, and the world gains a fragile shell that can bend trees and lace power lines. Types of rain differ by the microphysics that made them. Drizzle forms from tiny droplets spread evenly through low clouds, often in stable maritime air where collision is gentle. Convective showers, born in tall cumulus towers, deliver larger drops in sudden bursts as strong updrafts loft water high, then release it in pulses. Stratiform rain, tied to wide and layered systems, arrives as a patient curtain that can last for hours. Each pattern reflects the engine that built the cloud, the temperature profile beneath it, and the way air is moving at many heights at once. When sunlight meets falling rain, the sky writes with geometry. Light slows slightly as it enters water, bends by refraction, reflects from the inner surface, then bends again as it exits. The angles depend on wavelength, so red, with longer wavelength, leaves the drop at a slightly larger angle than blue. An observer facing away from the sun sees this separation as a ring of color that centers on the shadow of the head. A rainbow is not a single arc hung in air. It is a set of rays from countless drops that happen to send each color toward the eye. Move a few steps, and a different set of drops supplies the color, so the bow is new at every position. Secondary bows sometimes appear outside the first. They arise from rays that reflect twice inside the drop, losing brightness and reversing the order of colors. Between the two arches lies a darker band where fewer rays travel, called Alexander's band, a detail noted in ancient description and confirmed by modern optics. Under low sun, supernumerary fringes can shimmer just inside the main bow, interference patterns that reveal how uniform the drop sizes are in a passing shower. As the falling drop approaches the surface, air grows denser, temperature steadies, and the terminal speed relaxes. The landing can be quiet or abrupt. On a leaf, the drop spreads, pulls back into a bead by surface tension, then slips from tip to ground. On warm pavement, it can hiss and vanish. On soil, it sees a choice between infiltration and overland flow. The choice depends on the texture of the ground, the slope, the presence of roots, the intensity of the rain, and the recent memory of water already stored in pores. The first contact with dry ground carries a scent. When rain strikes earth after a long spell, oils from plants and soils are released, and bacteria known as actinomycetes give off geosmin, a compound the human nose can detect in minute concentrations. Wind lifts these aerosols ahead of the rain line, so the smell of wet earth arrives before the drops themselves, a sensory signal that weather is changing. Infiltration draws water downward through spaces between grains. Sandy soils accept water quickly, then allow it to drain. Clay holds water tightly, swells as it wets, and slows the flow. Organic rich loam, woven by roots and burrows, carries water through irregular channels called preferential flow paths that move it faster than the bulk soil would suggest. When rainfall exceeds the soil's capacity to absorb it, thin sheets of water gather and move downslope, a process called Hortonian overland flow. When the ground is already saturated and pores are full, any further rain is forced to run along the surface, called saturation overland flow. Where water enters rock, the story changes pace. Fractures and karst caverns can swallow a storm in minutes and move it far underground. There, water joins aquifers, vast natural reservoirs that store supplies for years, centuries, even millennia. Residence time stretches across human history, and a molecule can wait in darkness until pressure gradients gently urge it toward a spring. What falls in a single afternoon can reappear as a clear ribbon of water from a hillside years later. Even when water sinks, some returns to the air swiftly. Warmth from sun and soil evaporates thin films from leaves and stones. Plants draw water through roots and release it as vapor from stomata, a process called transpiration. Together, evaporation and transpiration, often combined as evapotranspiration, lift enormous volumes of water back into the lower atmosphere, where rising air will again carry it to condensation and cloud. The mean residence time of water in the atmosphere is roughly a week, so the vapor over any landscape turns over many times in a season. Rain that remains at the surface begins to gather. It finds shallow channels, then rivulets. It cuts tiny rills in soft ground, then feeds a stream. Drop by drop, a network takes shape, a branching web that follows slopes, geology, and the work of past storms. This organizing tendency from scattered beads to ordered flow is a hallmark of water across scales. While the drop falls and lands, energy moves with it. Condensation releases the latent heat that was hidden when water evaporated. This heat fuels updrafts inside clouds and helps build storms. On the way down, the drop surrenders potential energy, a small amount for each bead. Yet over a wide rain field, the total becomes significant, driving erosion that shapes slopes and carries sediments toward basins. Sound and touch complete the moment. Rain on metal roofs creates clear ringing, on forest canopy a soft hiss, on ocean a whisper that covers the sea with small dimples and rings. The character of the sound depends on drop size distribution and arrival rate. Gentle drizzle builds a steady noise that helps minds settle. Heavy showers add percussive beats and occasional taps from larger splashes that break into crowns and secondary droplets. The chemistry of the drop gives clues to its path. Marine showers may carry sea salt nuclei. Continental storms bring dust. Desert rains can carry fine loess that traveled hundreds of kilometers. In cities, sulfates and nitrates add slight acidity, a factor that many regions have reduced through cleaner fuels and scrubbed emissions. Within forests, dissolved organic compounds tint water a light tea as it runs from leaves and soil. Electricity threads through the larger cloud systems that produce downpours. Charge separation occurs as ice particles collide, larger graupel collecting negative charge while smaller ice crystals carry positive charge upward. Fields grow until discharge becomes lightning, heating air in a narrow channel to temperatures hotter than the surface of the sun for a brief instant. Thunder is the rolling response of air expanding and contracting along that channel. Rain that falls from such systems can arrive in bursts, structured by downdrafts and gust fronts that sweep across the land. Patterns of rain on Earth follow global engines. Near the equator, intense sun drives rising air and daily convection, building towering clouds that release afternoon showers. Between the subtropics and mid-latitudes, storm tracks follow the clash of warm and cold air along frontal systems, laying broad plumes of stratiform rain over land and sea. Monsoon systems shift with the seasons as land heats and cools faster than ocean, drawing moist flow inland for months, then reversing. Topography adds its signature. Mountains lift moist air, squeeze out water on windward slopes, and cast dry rain shadows on the leeward side. Local triggers can be small. A dark, plowed field warms faster than surrounding grass, starting a weak thermal that becomes a cloud seed. A lake steams on a cold morning and feeds a low deck of stratus. City heat and roughness alter breezes and can focus afternoon showers along convergence lines. Each raindrop therefore carries the imprint of scales from global circulation to the warmth of a single roof. The quantity of water on Earth is effectively constant across human eras. It moves through forms and reservoirs, ocean, ice, lakes, soil, atmosphere, living tissue. The same molecules that fell on ancient ferns still circle through storm and stream. A molecule may have been part of a Devonian sea, later enclosed in a glacier, later breathed out by animals on a tropical plain, later condensed as a drop that kissed the surface of a city window. Though the total remains steady, the distribution changes with climate. Warming air can hold more vapor, roughly 7% more per degree Celsius, a relationship described by the Clausius-Clapeyron curve. This capacity shifts the odds toward heavier, short-duration rain events in many regions, even as some areas see longer dry intervals between storms. Land management shapes outcomes as well. Forests that intercept and infiltrate versus hard surfaces that accelerate runoff. The path of each drop is shaped by physics, weather, and human choice. When the drop finally meets open ground, three fates dominate. It can evaporate back to air within minutes, closing a loop that began only hours earlier. It can infiltrate and join slow underground flow, entering a chapter measured in seasons or centuries. Or it can travel across the surface, finding the nearest hollow and beginning a quick journey toward a creek. Whatever the route, no molecule is lost. It only moves. The first stage of the journey, from cloud to ground, reveals how intimately life is linked to air. Rain does not arrive from elsewhere. It is part of the planet's breath. The atmosphere exhales moisture into droplets. The land inhales it through soil and stream, then returns it to sky as vapor. This breathing never pauses, only changes tempo with season and place. Time. Threes. Each drop is small, yet the work is large. Canyons deepen one storm at a time. Soils renew as minerals travel from rock to root. Lakes rise and recede with the rhythm of clouds. Rivers learn their shapes from the memory of many rains. Shorelines shift, deltas build, and wetlands pulse as they trade water with sky. Water is the great traveler of Earth. It dissolves, transports, cools, and sustains. Inside every organism, inside every leaf and lung are molecules that have fallen as rain more times than can be counted. The same order that gathers droplets in a cloud also gathers life along rivers and coasts, where abundance follows the path of flow. The journey of this chapter closes where gravity and ground first meet. A raindrop lands on a leaf, slides to a stem, pauses on a ridge of bark, leaps to soil, and chooses a dark path downward. Another lands on stone and flashes back to air. Another reaches a shallow hollow and waits until many arrivals form a silver skin that starts to move. The cycle has no beginning, and no end, only motion. In the next part of the story, the raindrop's path continues across the surface of the earth, into rivulets and streams, through gathering rivers that bend toward the sea. At the river's mouth, the fresh water that once fell as rain meets the salt water of the sea. The transition is not abrupt. It happens gradually across a region called an estuary, where tides mix the two in endless motion. The estuary is a place of change. Salinity rises and falls with every tide. Sediment carried from land settles here, forming mudflats and wetlands rich in nutrients. In these shallow waters, microscopic plants called phytoplankton use sunlight to convert carbon dioxide into oxygen, forming the base of the ocean's food web. Here, the raindrop becomes part of a vast system. Molecules of fresh water blend with salt, carried by gentle tides into the open sea. Once in the ocean, the drop joins a body of water that covers 70% of Earth's surface and holds 97% of its total water. The ocean is a continuous world. Its boundaries are human creations. Names like Atlantic, Pacific, and Indian mark regions of one connected system. Currents, driven by wind, heat, and the rotation of the planet, move water across thousands of kilometers. A single molecule may circle the globe, from polar ice to tropical shallows, over centuries. The upper layer of the ocean, where sunlight can still penetrate, is known as the photic zone. It extends down to about 200 meters. Here, light supports photosynthesis, feeding the microscopic life that forms the foundation of marine ecosystems. Most visible ocean life, fish, corals, and plankton, exists within this thin, illuminated layer. Beneath it lies the twilight zone, where light fades and colors disappear. Below 1,000 meters, darkness is complete. Pressure increases with every meter, and temperature drops close to freezing. Yet even in this deep, silent realm, life persists, adapted to darkness, slow movement, and cold. The ocean is structured not only by depth, but also by temperature and salinity. Warm water from the equator and cold water from the poles interact to form layers of density. These layers rarely mix completely. The surface changes quickly with wind and weather, while the deep ocean moves slowly, driven by differences in temperature and salt content. This slow global motion is called thermohaline circulation, from the Greek words for heat and salt. It acts like a conveyor belt connecting all the world's oceans. Warm, surface water flows northward, releasing heat into the atmosphere. As it cools and becomes saltier through evaporation, it sinks, traveling along the seafloor toward the equator before rising again. A single, complete circuit may take 1,000 years. The energy that moves this circulation comes from sunlight. Solar radiation warms the equator more than the poles, creating differences in temperature that drive winds and ocean currents. These currents distribute heat around the planet, moderating climates and making Earth habitable. When the raindrop joins the ocean, it becomes part of this vast exchange. It may be carried east or west by surface currents, such as the Gulf Stream in the Atlantic, or the Kuroshio Current in the Pacific. These rivers within the sea transport warm water toward colder regions, influencing weather far inland. As wind moves across the surface, it transfers energy to the water, creating waves. Each wave represents energy passing through water molecules, rather than the motion of the water itself. A floating object, like a leaf or a buoy, rises and falls, but does not travel far horizontally. This subtle movement connects every drop to the energy of the sky above. Waves vary from gentle ripples to swells that cross entire oceans. Storms generate larger waves that can travel for thousands of kilometers before reaching shore. When these waves meet shallow land, their lower edges slow while the upper parts continue forward, causing them to rise and break, the rhythmic motion that defines coastlines. Within the ocean, temperature and light define zones of life. Near the surface, phytoplankton thrive, forming the base of a food chain that supports fish, whales, and seabirds. In deeper layers, creatures adapt to darkness and scarcity. Bioluminescent organisms create their own light, illuminating the deep in brief electric flashes. Water carries more than life. It stores and moves energy. The ocean absorbs about 90% of the excess heat generated by human activity. It also takes in carbon dioxide, buffering the planet's climate but gradually becoming more acidic as a result. Each drop of seawater plays a role in this global balance. The salt that fills the ocean comes from the land. Over millions of years, rain and rivers have dissolved minerals from rocks, carrying them to the sea. Evaporation removes pure water, leaving the salts behind. Sodium chloride, the same compound as table salt, makes up most of this mixture. Its concentration averages about 35 grams per liter. Despite its vastness, the ocean is in constant communication with the atmosphere. Water vapor rises from its surface, forming clouds that will later release rain. The same process that began the raindrop's journey continues here, powered by the heat of the sun and the cool of the night. Tides move in predictable rhythm, caused by the gravitational pull of the moon and the sun. As the Earth rotates, different regions of the ocean bulge slightly outward, creating the rising and falling of water along coastlines. These movements mix nutrients, stir sediment, and shape the lives of countless marine species. Near coastlines, the raindrop may rise again to the surface. Sunlight warms it, and wind stirs it toward the air. Some of its molecules evaporate, returning to vapor. Once more, they begin to ascend, carried by convection into the atmosphere. The journey that began in a cloud approaches its completion. But many other molecules remain below, moving with deep currents. They may circle the globe before returning to the surface. Some will freeze into polar ice, locked for centuries in glaciers. Others will join the evaporation cycle within days. Time moves differently in the sea, slow and vast, marked by tides and seasons rather than minutes or hours. The surface of the ocean reflects light from the sun and the moon, while beneath it lies a world of hidden motion. Temperature gradients, salinity shifts, and undersea ridges guide water in patterns as intricate as wind in the atmosphere. Satellites and buoys now map these invisible roads, revealing how deeply connected the ocean truly is. Where warm and cold currents meet, life flourishes. Nutrients from deep water rise to the surface in a process called upwelling, feeding plankton blooms that sustain fish populations and seabirds. The meeting of currents shapes climate, rainfall, and even the growth of forests thousands of kilometers away. Through the ocean, the raindrop joins not just water, but energy, carbon, and life itself. The sea breathes with the planet, exchanging gases with the air, releasing and absorbing heat, and creating the moisture that will one day fall again as rain. The path from river to ocean is therefore not an end, but a transformation. The same molecules will rise, fall, and flow countless times, linking every ecosystem and every breath. The raindrop that once touched the soil now becomes part of the pulse that governs weather, temperature, and life across the entire Earth. In the next part of this story, the journey turns inward, into the unseen water that moves through living things. From plants to animals, from forests to human bodies, the same molecule continues its quiet passage through the network of life. After falling from the cloud, the raindrop lands upon the surface of the earth. Its path from this moment can take many forms. Some water returns immediately to the air through evaporation. Some is absorbed by the soil, feeding the roots of plants. Some begins to move slowly across the surface, drawn by gravity toward lower ground. When rain meets soil, it begins to interact with the living world. The uppermost layer of soil, rich in organic matter, holds water like a sponge. This moisture supports fungi, bacteria, and microscopic life that sustain the fertility of the land. Every forest and field depends on this thin layer, where air, mineral, and water meet. If the soil is saturated or covered with stone, the raindrop begins to flow across the surface instead of soaking in. This movement forms a thin film called runoff. As many droplets follow the same slope, their combined motion carves small channels in the ground. Over time, these channels merge, creating trickles, then streams. The first centimeters of flow shape what follows. On gentle ground, water spreads and travels as sheet flow before lines of weakness collect it into rills. On steeper slopes, gravity sharpens the descent and rills bite into soil to form gullies. Vegetation slows this process by roughening the surface, its roots stitching the earth so raindrops do not easily dislodge grains. Where plants are sparse, each impact frees a few particles, and the next shower carries them farther down slope. Streams are among the oldest features on the planet's surface. They shape landscapes through erosion and transport, gradually carrying sediment from higher to lower elevations. Each grain of sand or clay they move becomes part of a greater migration of material. Valleys, plains, and deltas owe their existence to the steady motion of flowing water. At the headwaters of a watershed, channels are narrow and steep. Water runs swiftly over rock steps and through shaded hollows. In these upper reaches, flow alternates between cascades and pools, a rhythm set by boulders, fallen logs, and bedrock ledges. Shear stress on the bed is high, so coarse fragments move during storms, grinding and rounding as they tumble. As streams descend, their gradient eases and power spreads across wider beds. Sediment begins to sort itself by size. Coarser grains settle first, while fine silts stay in suspension. The channel develops bars of sand and gravel, then bends and curves that signal a transition from incision to redistribution. The geometry of bends follows a quiet logic. Water, moving around a curve, flows faster on the outside bank, where the path is longer, and slower on the inside. Faster water scours and undercuts. Slower water lays down sand. Point bars build on the inner edges, while cut banks retreat on the outer edges. Over years, the whole pattern migrates laterally, a river writing its history across a floodplain. Within any reach, the current is not uniform. Surface ribbons move quickly, near bed layers creep, and eddies swirl behind stones. Small zones of calm water, called refugia, allow insects and fish to rest between bursts of movement. The raindrop that joined the stream now drifts, accelerates, and turns in these patterns, sometimes lingering in backwaters before rejoining the main flow. Rivers are more than moving water. They are living corridors that connect mountains to oceans. In their channels live caddisflies that build cases from sand grains, mayflies that graze on algae, and stoneflies that require cold, clean water. Minnows flash in schools near the surface, while trout hold in the seams where fast and slow water meet. Along the banks, willows and alders draw moisture from shallow groundwater, tying soil with roots and shading the stream with leaves. The chemistry of the river evolves as distance grows. Rainwater that was nearly pure gains dissolved ions from rock, such as calcium from limestone and silica from granite. Carbon dioxide from air and soil mixes in, forming weak carbonic acid that helps weather minerals. As water passes through fields and forests, it collects nutrients that fuel growth downstream. In healthy reaches, wetlands and floodplains act as filters, trapping excess sediment and transforming some nutrients back into harmless forms. Each river belongs to a watershed, an area of land where all precipitation drains to a common outlet. Watersheds vary from hillside hollows to continental basins. Ridges and divides guide the paths unseen. A raindrop landing a few meters one way may head toward a distant sea, while another, falling just beyond a crest, may find a completely different ocean. The motion of a river changes with season and weather. During snowmelt, cold torrents rush through mountain valleys. During summer drought, shallow riffles blink with sunlight and expose polished stones. Floods spread across floodplains, laying a thin sheet of silt that replenishes soils. Recession follows, and side channels become quiet lagoons where young fish find shelter. Flow is measured not only by speed, but by discharge, the volume passing a cross-section each second. A single thunderstorm can double the discharge of a small creek, while in great rivers a monsoon can raise levels by meters over vast widths. The hydrograph, a curve of flow against time, preserves these pulses as memory. Meta, pause. Sex, 3.0. Pitch, 1%. Underground, part of the rain that seeped through soil continues a slower journey. Gravity draws it down until it meets rock of low permeability. There, water collects in aquifers, hidden reservoirs that may take decades or centuries to fill. Through pores and fractures, the water moves centimeters per day, guided by differences in pressure. Springs appear where these paths intersect the surface, feeding headwater streams even when skies remain clear. This connection between surface water and groundwater sustains rivers through dry seasons. Base flow from aquifers keeps channels alive when rain is absent. The temperature of such water is buffered by the ground, cool in summer and mild in winter, providing stable conditions that many species depend on. When groundwater is withdrawn faster than it is replenished, streams shrink, wetlands dry, and the web of life tightens. Human history follows rivers closely. Ancient settlements rose on floodplains where seasonal inundation renewed fertility. Agriculture organized itself to the rhythm of rising and falling waters. Boats turned channels into roads, and trade spread ideas along with goods. Names on maps preserve this lineage, with cities bearing the marks of bays, fords, and deltas. Modern engineering learned to harness flow with dams, levees, and canals. Reservoirs provide drinking water, irrigation, and hydropower. Locks step ships across changes in elevation. At the same time, these structures alter the natural cadence of flood and drought, reduce the delivery of sediment to coasts, and create barriers to fish whose life cycles once depended on free passage. The balance between use and health relies on careful releases, bypass channels, and protected floodplain space. The shape of a channel reflects the load it carries. Bedload consists of sand and gravel that rolls and hops along the bottom. Suspended load consists of finer silt and clay that rides the flow. Dissolved load is invisible to the eye, minerals carried as ions. When discharge rises, the river can lift larger grains, rearranging bars and riffles in a single night. When flows fall, the coarser fraction remains, and the bed roughens. Meanders arise where banks can erode, and where vegetation does not lock the planform in place. The radius of curvature scales with channel width, and the distance between bends follows a repeating pattern. Over time, a bend can tighten until the river breaches the neck during a flood. The old loop becomes an oxbow lake, a crescent of calm water that hosts lilies, frogs, and dragonflies. Floodplains are part of the river itself. They store water temporarily, lowering flood peaks downstream. They host forests and meadows adapted to periodic inundation and grow soils from layers of silt. When levees confine a river tightly, this storage is lost, and high water runs faster and higher, shifting risk rather than removing it. Restored floodplains and side channels return space to the river and resilience to communities. Along many coasts, deltas mark the meeting of river and sea. Here, the channel slows, drops its load, and splits into distributaries. Sediment builds land outward in lobes that advance into shallow water. Marshes and mangroves anchor this new ground, buffering storms and providing nurseries for fish and birds. If sediment supply is cut or the sea rises too quickly, deltas subside and retreat, reminding all that land at the water's edge depends on a continuing gift from upstream. Water temperature and clarity tell the story of a river's path. Cold, clear mountain streams carry high oxygen and support organisms that need it. Farther downstream, where sunlight warms broad channels, aquatic plants thrive and provide habitat for amphibians and birds. After storms, suspended sediment turns water the color of tea or clay. As particles settle, clarity returns and light again reaches the bed. Riparian forests knit land to water. Their roots resist erosion, their leaves shade channels, and their fallen limbs create pools where fish rest. When a mature tree leans and topples, it becomes large wood that deflects flow, shapes bars, and captures sediment. Insects drop from branches, feeding fish. Birds nest in the tangle above the current. The boundary between river and forest is porous and alive. Wetlands adjacent to rivers act as kidneys for the landscape. Slow water allows particles to settle and fosters microbes that transform nitrogen compounds, reducing the nutrient loads that could otherwise bloom downstream. These broad, quiet places store floodwaters and release them slowly, smoothing the hydrograph. They also recharge aquifers beneath, linking surface storage to underground reserves. Where glaciers still feed headwaters, meltwater contributes a milky hue from rock flour ground fine beneath moving ice. In arid basins, ephemeral streams wake only after rare storms, advancing as shallow fronts that soak into dry beds until the channel wets through. In karst terrain, rivers vanish into swallow holes and travel unseen before emerging as blue springs. The raindrop meets many terrains, and each terrain writes a different chapter. Water quality mirrors land use. Forested basins tend to yield cool, clear flows. Agricultural valleys contribute nutrients and fine sediments if buffers are missing. Cities add complexity with storm drains, road runoff, and warm water from sunlit streets. Green infrastructure, such as rain gardens, permeable pavements, and detention ponds, slows and filters this pulse so that rivers receive water that is cleaner and closer to the timing nature expects. In mountain canyons, the energy of floods can rearrange landscapes in a single night. Debris flows surge with a slurry of boulders and mud released from steep slopes. In lowlands, the same storm becomes a broad rise that overtops banks slowly and spreads over fields. Different hazards, same origin. Many raindrops arriving together with more speed than channels can carry. Preparedness grows from maps that remember history and from rooms set aside where water can safely wander. As the river approaches a plain, it slows and begins to wander. Bends tighten, scroll bars record former paths, and oxbows dot the floodplain like mirrors of the sky. The channel becomes a mosaic of riffles that aerate water and pools that store it. Fish move among these habitats with the seasons, seeking cool depths in summer and sunlit shallows in spring. Eventually, the river widens toward its mouth. Tides begin to tug at the current, reversing flow twice each day in the lower reaches. Fresh water rides over salt along a subtle boundary called a halocline, and mixing creates layers that slip past each other. Sediments settle in quiet pockets, building mudflats that host shorebirds on their long migrations. Estuaries are among the most productive ecosystems on Earth. Nutrients from land meet the energy of tides and the shelter of marshes. Phytoplankton bloom, feeding zooplankton, which feed small fish, which feed larger fish and birds. Grasses, reeds, and mangroves trap sediment and turn sunlight into living tissue that supports a web of life few places can match. Here, the raindrop that began in a cloud finds salt. It may linger in brackish creeks, circulate with the tide, or slip along the bottom as denser water encroaches upstream. Eventually, it enters the open sea, where currents carry it onward. The cycle has reached a threshold, not an end. Even after the raindrop enters the sea, its passage continues. Wind curls the surface into waves that mix the upper ocean. Sun warms a thin skin by day, and night cools it again. Some of the water rises as vapor within hours. Some joins currents that circle basins for years, and some sinks with cold, salty water to travel great distances in the deep. Through this long journey, water shapes the surface of the earth and sustains its balance. Every stream, river, and delta is a record of time, a living archive of how the planet breathes. The same molecule may serve a leaf, a fish, a cloud, and a glacier. Yet it is always water, moving according to quiet rules that link sky to soil and mountain to sea. Time threes. The chapter at the surface closes where fresh water meets tide. The work of gravity has carried the raindrop from slope to channel, and from channel to plain. The work of sunlight will lift it again. Between those forces lies the story of rivers, patient shapers of land and keepers of life. In the next part of this story, the raindrop enters the vast and changing ocean, where currents, temperature, and light guide the next passage through the cycle of the world's waters. Share in the comments where you listen from and what you would like this journey to explore next. Water is not only the substance of rivers and oceans, it is the medium of life itself. Every living organism, from the smallest bacterium to the largest whale, depends on it for structure, transport, and energy. After entering the sea, part of the raindrop's water will eventually rise again into the sky. Another part continues inward, drawn into the tissues of plants and animals that live near the coast or far inland. Wherever life exists, water is present. In plants, water begins its path in the soil. Roots absorb it through microscopic hairs that extend into the spaces between grains of sand and clay. Within each root, water moves upward through narrow tubes called xylem. The force that pulls it comes partly from evaporation at the leaves, a process called transpiration. When sunlight warms the leaf surface, water vapor escapes through tiny pores called stomata. This loss of moisture creates a slight negative pressure that draws more water upward from the roots. In this way, a continuous column of water links soil to sky. Each molecule participates in a chain that can rise tens of meters within a tree. Along its journey, the water carries dissolved minerals such as calcium, potassium, and magnesium. These nutrients support photosynthesis and growth. Inside the leaf, water also serves as the medium in which carbon dioxide reacts with light to produce sugars. Without this fluid connection, plants could not store or exchange energy. Through transpiration, plants release vast quantities of moisture into the atmosphere. A single large tree can release hundreds of liters of water each day. Forests, acting together, return enormous amounts of vapor to the air, forming clouds and influencing regional rainfall. In this way, vegetation and atmosphere form a single breathing system. When animals consume plants or drink from rivers, they join this cycle. Inside every animal body, water becomes the solvent of life. It dissolves nutrients, carries oxygen, removes waste, and regulates temperature. In most mammals, water makes up about 60% of body mass. Blood is mostly water mixed with cells and dissolved salts. It travels through vessels, delivering oxygen and collecting carbon dioxide for release through the lungs. Within cells, water surrounds every protein and molecule, maintaining shape and enabling chemical reactions. The human body itself demonstrates the continuity of the water cycle. Every breath releases moisture into the air. Every drop of sweat and every exhaled vapor returns a small portion of the body's water to the atmosphere. The same molecules that once fell as rain leave again to become part of a cloud. In living tissue, water has unique physical properties. Its ability to absorb heat without rapid temperature change stabilizes body temperature. Its surface tension allows blood to flow smoothly through capillaries only a few micrometers wide. Its polarity enables the formation of hydrogen bonds, giving it the power to dissolve and transport almost any substance essential for life. Many organisms have evolved to use water efficiently. Desert plants store it within thick stems. Frogs and fish absorb it directly through their skin. Even in arid regions, microscopic life survives within thin films of moisture that coat grains of soil at dawn. Water also shapes behavior and migration. Animals follow seasonal rains, moving between habitats as rivers swell or shrink. Birds navigate along routes defined by wetlands and lakes. Insects time their breeding cycles to coincide with the return of monsoons. Inside ecosystems, water acts as a messenger of energy. When sunlight warms a leaf or a pool, water evaporates and carries heat into the atmosphere. When it condenses into rain, it releases that heat again, influencing weather and climate. The same molecule that nourishes a plant today may shape tomorrow's clouds. Humans have always depended on water's predictability. Early settlements grew near springs and rivers. Agriculture emerged where rainfall and irrigation could sustain crops. Modern cities still trace the patterns of ancient watercourses, even when the rivers themselves have been redirected underground. The use of water connects technology and ecology. We draw it from aquifers, purify it for drinking, and return it through treatment systems. Each step alters its chemistry slightly before it rejoins the natural cycle. Water reminds humanity that resources are not isolated. They circulate continuously between natural and human systems. Within the oceans, water sustains life of astonishing variety. Phytoplankton use it to capture sunlight and form the base of marine food chains. Fish extract dissolved oxygen through their gills. Whales filter countless liters each day as they feed, passing the same molecules through their bodies and back to the sea. Even icebound regions hold life within liquid veins that flow between crystals. Bacteria and algae survive there, using tiny amounts of dissolved nutrients. When spring comes, the melting ice releases this life back into the ocean, continuing the exchange. Through all these processes, the water from a single raindrop may pass through thousands of organisms before returning to the sky. It may rise as vapor from a leaf, exhale from an animal's lungs, or drift upward from the surface of the sea. In each transformation, it serves as both carrier and participant in life's chemistry. The balance of this cycle is delicate. Deforestation, pollution, and rising temperatures can alter how water moves between land, air, and living systems. When vegetation is lost, less moisture returns to the atmosphere, and rainfall patterns shift. When oceans warm, evaporation increases, changing weather around the world. Understanding the role of water within life is therefore also understanding the balance of the planet. Each drop contributes to temperature regulation, nutrient exchange, and the creation of energy in ecosystems large and small. The continuity of life depends on the continuity of water. From the soil beneath forests to the cells within the human body, water's path is one of unity. It binds the physical and the biological, linking geology, atmosphere, and living tissue in a single circulation. In the next part of this story, the journey turns outward again, to the atmosphere that receives this vapor, the clouds that form from it, and the global patterns of weather that complete the water's eternal cycle. After its long passage through rivers, oceans, and living things, the raindrop begins to rise again. This return to the atmosphere marks the next stage of the water cycle, evaporation. Driven by heat from the sun, molecules of water gain energy, move faster, and escape from the liquid surface into the air as vapor. Evaporation occurs everywhere water is exposed to air. It happens on ocean waves, on lakes and soil, on leaves, and even from the surfaces of rocks that hold thin films of moisture. The process is continuous and invisible, forming the connection between the surface of the planet and the sky above. At the same time, plants release water through transpiration. Together, evaporation from surfaces and transpiration from vegetation are known as evapotranspiration. This combined process returns nearly all of the water that falls as rain back to the atmosphere. The energy that drives evaporation is solar radiation. Sunlight warms the oceans and land, providing the energy needed to break the bonds between water molecules. Each gram of water that evaporates carries with it latent heat, energy stored in the vapor. When that vapor later condenses into clouds, the same energy is released, powering the movement of air that creates weather. Warm air can hold more water vapor than cold air. As moist air rises and cools, it reaches a point known as the dew point. At this temperature, the air can no longer contain all of its moisture, and condensation begins. Tiny droplets form around particles of dust or salt, becoming the seeds of clouds. These clouds drift with the wind, changing shape as they gather or lose moisture. Cumulus clouds form when air rises rapidly, creating cotton-like shapes. Stratus clouds spread in flat layers, signaling stable air. Cirrus clouds form high above, made of ice crystals that glint in sunlight. Each type reflects a balance between temperature, humidity, and wind. As clouds grow, they become part of larger weather systems. When the sun heats the surface unevenly, warm air rises in some regions, and cooler air sinks in others. This movement sets up convection currents that organize into pressure zones. High pressure brings clear skies. Low pressure draws in moist air, creating clouds and rain. Large-scale patterns of air circulation shape global weather. Near the equator, warm air rises and moves toward the poles. As it cools and descends, it forms belts of wind known as trade winds and jet streams. These patterns shift slightly with the seasons, carrying clouds and storms along predictable paths. In tropical regions, evaporation from warm oceans fuels powerful weather systems such as monsoons and cyclones. Monsoons occur when continents heat and cool differently from the surrounding sea. During summer, warm air over land draws in moist ocean winds, bringing months of heavy rain. Cyclones and hurricanes form over warm water when rising air spirals around a center of low pressure, releasing enormous amounts of latent heat. At higher latitudes, fronts form where warm and cold air masses meet. The lighter, warmer air rises over the denser, colder air, causing moisture to condense into clouds and rain. The energy released during condensation fuels the movement of these systems, driving the wind and shaping local climates. Through all these processes, water acts as Earth's main carrier of energy. It transfers heat from oceans to atmosphere and from tropics to poles. Without this continuous circulation, the planet's temperatures would vary far more sharply, and life would struggle to adapt. As vapor condenses, droplets collide and grow. When they become heavy enough, gravity pulls them downward again as precipitation, rain, snow, sleet, or hail. The form depends on temperature through the layers of air the droplet passes. Each fall renews the surface below and restarts the cycle that has continued for billions of years. Not all water that evaporates returns as local rain. Moisture can travel thousands of kilometers before falling again. Air currents carry it from oceans to continents, across mountains, and into deserts. This transport of vapor links climates across the globe, ensuring that even distant ecosystems depend on the same planetary circulation. Over forests, much of the rainfall that falls returns quickly to the sky through transpiration. Over oceans, evaporation exceeds precipitation, while over land, the balance is reversed. The excess water that falls on land eventually flows back to the sea, maintaining a stable global system. The cycle is continuous but not uniform. Seasonal shifts, volcanic eruptions, and human activity all influence the distribution of heat and moisture. When forests are cleared, local evaporation decreases, and rainfall patterns can change. When greenhouse gases warm the atmosphere, evaporation increases, intensifying storms and altering climates. Despite these variations, the principles remain the same. The energy of the sun drives evaporation. Gravity returns water to the ground. Temperature and wind guide its path through the air. Together, these forces create the rhythm of rain, wind, and cloud that shapes every landscape on Earth. Water vapor also plays an important role in regulating temperature. It is the most abundant greenhouse gas in the atmosphere, trapping heat radiated from the surface. This feedback maintains a balance that keeps the planet's average temperature within the range suitable for life. From a global perspective, the movement of water defines weather and climate. The rising of vapor from the ocean, the gathering of clouds, the fall of rain, and the flow of rivers form one continuous circulation, the hydrologic cycle. Every drop participates in it, whether it falls on a mountain, an ocean, or a human hand. When viewed over time, this cycle has sculpted continents, shaped ecosystems, and sustained evolution. Through evaporation and rain, erosion and flow, water connects the physical and biological worlds. The air we breathe and the soil that feeds us are both products of its work. As the raindrop that began this story ascends once more into the clouds, it carries with it the memory of its long passage through rivers, oceans, and living things. Soon it will join billions of others, condense into a new cloud, and fall again somewhere else on the planet. In the next and final part of this journey, the story turns to reflection on what the water cycle reveals about the balance of the Earth and about the quiet connection between every form of life that depends on it. The journey of a raindrop is never truly finished. From its first moment as vapor to its fall as rain, its flow through rivers, and its return to the sky, it remains part of a single, unbroken circulation. This continuity defines the rhythm of the Earth. The total amount of water on the planet has remained nearly constant for billions of years. What changes is its form and its location. At any moment, about 97% lies in the oceans, 2% in ice and snow, and less than 1% in rivers, lakes, and the atmosphere. Yet that small fraction moving through air and land sustains every living thing. Each molecule cycles through many states, liquid, vapor, and solid, sometimes within hours, sometimes across millennia. Water that once fell as rain over mountains may now flow as groundwater beneath forests or drift as vapor above the equator. In this circulation, the boundaries between sky, land, and life disappear. The water cycle links every ecosystem. Rain feeds soil and rivers. Rivers feed oceans. Evaporation renews the clouds. Plants release moisture. Animals return it through breath, and the atmosphere gathers and redistributes it again. The system operates without pause, powered by sunlight and guided by gravity. This constant motion maintains balance across the planet. Evaporation cools surfaces by carrying heat upward. Condensation warms the air as clouds form. Precipitation returns minerals to the soil and cleanses the atmosphere of dust and particles. Even the smallest event, a drop landing on a leaf, participates in this global exchange of energy and matter. Through geological time, the movement of water has shaped the face of the Earth. It carved valleys and canyons, built deltas, and carried sediment to form new land. Mountains erode slowly under its touch, while coral reefs rise through the accumulation of marine life that depends on its chemistry. Every landscape carries the signature of flowing water. The cycle also connects the deep past to the present. The water that falls today is ancient. Some of it may have evaporated from oceans millions of years ago, frozen in polar ice, or traveled underground through layers of rock before returning to light. Every raindrop is a fragment of that vast and continuous memory. In the biosphere, water acts as both foundation and messenger. It transports nutrients, distributes heat, and provides the medium for every biochemical reaction. Life could not exist without it, and it, in turn, is shaped by life. The movement of water through forests, plankton, and clouds demonstrates how the living and the physical are one system. This connection makes the water cycle not just a physical process, but also an ecological balance. When one part is disturbed, through deforestation, pollution, or climate change, the effects ripple across the entire system. Reduced vegetation means less moisture released to the air. Warming oceans produce stronger storms. Shifts in rainfall influence crops, wildlife, and human settlements. Understanding the water cycle reveals how deeply interdependent Earth's systems are. No species, climate, or landscape exists in isolation. Each is bound to the others through this silent, continuous exchange. Every drop of rain carries that message of connection. The same physical principles that guide this circulation, energy, pressure, and gravity, operate throughout the universe. Yet on Earth, they combine in a way that sustains life. Water's unique properties, its ability to dissolve substances, to expand when frozen, and to store heat, make the planet stable and habitable. Humanity depends on this equilibrium. Agriculture, industry, and health all rely on predictable patterns of rain and evaporation. Clean water is essential for every community, yet it remains finite and shared. The challenge of the future is to manage it wisely, to understand that every river, cloud, and storm belongs to one global system. Technology now allows us to see the water cycle from space. Satellites measure rainfall, track clouds, and map the flow of oceans. These images reveal a living planet, blue, bright, and interconnected. The patterns visible from orbit are the same that a single raindrop experiences during its passage from sky to sea and back again. The water cycle also serves as a reminder of resilience. No matter how many times it changes form, water always returns. It adapts to temperature, pressure, and time, yet its essence remains unchanged. It is the element of renewal, carrying the potential for life wherever it flows. In understanding this, there is a quiet comfort. The water that falls on a field, that fills a cup, that drifts as vapor into the sky has been part of the same endless circulation since the dawn of the planet. Every living thing is connected by it, sustained by it, and eventually returns it to the world. When Iod viewed in this way, the journey of a single raindrop becomes more than a story of movement. It is a reflection of balance between heat and cold, gravity and vapor, the physical and the living. It shows how simple forces acting together create complexity and harmony. The cycle continues at this very moment. Clouds form above the ocean, rain falls on mountains, rivers flow to the sea, and vapor rises again. The process has no beginning and no end. It is the quiet heartbeat of the planet. Through every stage, sky, land, sea, and life, the same molecules travel endlessly. They remind us that the world is not made of separate parts, but of connections. To understand water is to understand continuity, patience, and renewal. The next time rain touches the ground, it will begin this journey once more, downward, outward, inward, and finally upward again. The same timeless motion that cools the earth, nourishes life, and shapes the face of the planet will continue, drop by drop, breath by breath. The journey of a raindrop is the journey of the earth itself, a cycle of transformation guided by the calm, persistent rhythm of nature. Thank you for listening, and may your night be peaceful and still beneath the quiet rhythm of rain.